All right, guys, I want to give you a little bit of background on atoms and how they connect with some of these other things that we're looking at too. So let me just get this loaded up. Maybe. Okay, there we go. And for my unit, we're connecting this to static electricity. We've heard of static electricity, and we understand kind of what it is, but do we really know why it happens? So that's what we want to really look at in this unit, is the why of some of these questions. So first of all, come on. Okay, history of the atom. I'm going to walk you through the history of the atom just so you understand how the model has changed over time. And I want you to keep in mind that it's really important in science to remember that sometimes you can have a correct answer, but it becomes incorrect later. So Dalton wasn't wrong. That was a good model based on the scientific information we had at the time. But when scientific information changes, we have to change our model. So first of all, Dalton and some Greek philosophers believed that the atom was the smallest thing on Earth. That everything was basically made of atoms, and the root word of atoms, atomos, is Greek for indivisible. So he believed that this couldn't be broken down into anything smaller than an atom, that an atom of aluminum and an atom of gold are different from each other, but you can't go any smaller than an atom of aluminum. There's nothing inside an atom of aluminum. So that's what we thought for a long time. And then a gentleman did this experiment here. So what he did was he shot basically a gas in here. And if the atom was the smallest thing, then it should shoot straight through because there's nothing inside of it. It's indivisible, nothing inside of it, etc. So what they did was they placed a magnet on the side here. So you can see the positive side here, the negative side there. So there's a magnet there. And he noticed that every time it kept going towards the positive side. Every single time. If he switched the magnet and put the positive side on the top, it still went towards the positive side. So what goes towards a positive thing? A negative thing. So he figured out there's something negative inside the atom. The atom actually is divisible. There's something smaller than it. And he discovered the electron, the negative charge inside the atom. Okay. And he basically theorized, okay, well, if this thing is neutral, I know this thing is neutral that I put inside it, and I just discovered that there's something negative in there, there must be something positive in there too. But he didn't know exactly how or what or why, but he figured there must be something positive too. So he came up with, that was Thomson, by the way, he came up with what he called the plum pudding model, but probably none of you have ever had plum pudding. So I call it the chocolate chip cookie model. Okay. So he has electrons. Those are your chocolate chips. And we don't precisely put the electrons and the chocolate chips in certain places. He says, I think those electrons are randomly placed inside the atom. So there's not like organization to it, just like we don't randomly place chocolate chips in a cookie. But the majority of the cookie is a cookie dough. And same thing with the atom, though he thought that the majority of the atom is positive. So it's kind of this like loose positive thing with these random negative things. That's what he came up with as his model. So that was the model for a few years. And then his buddy Rutherford, so that's the Thomson model, his buddy Rutherford actually improved upon the model. So Thomson's model looks something like this. Remember that pink is like showing the positive and the blue are the electrons. And he did what's called the gold foil experiment. Rutherford did. He did the gold foil experiment. So what they thought would happen is, for the most part, this would shoot straight through. The reason they thought it would shoot straight through is because they basically felt like the positive part wasn't very strong. So it wasn't strong enough to pull onto anything inside. So they thought it was kind of this weak positive thing and then these strong negative things. So he figured they should be able to shoot pretty much straight through. That's not what happened. Almost the opposite is what happened. A lot of them shot straight through, but there was a chunk of space where they would rebound. And so you can kind of see here, sometimes it would rebound like right back. Sometimes it would angle off of the side. And so he discovered, you know what? I don't think the whole thing is positive. I think just a little section is positive, but it's strongly positive enough that you can actually reflect off of that. So Rutherford is the one who figured out that positive thing that we now call protons is actually centered in a nucleus. It's the center of the atom. All that positive part is inside that nucleus. Okay, so that's the first thing he discovered. The second thing he figured out was he agreed that there were electrons in here. Notice this one here, that it got attracted to the electron. So it kind of like sucked it towards the electron. And so you see that a slight difference of angle, and you can see that down here too. So he's like, okay, cool. The electron attracts it. So he shoots a beam at that same spot. And the second time he shoots it there, it doesn't attract like that. So what that tells us is these electrons are not like chocolate chips. They're not locked in place. Those electrons are actually moving around. So he came up really with three things. Okay, first of all, there is a positive part. It's densely packed in the nucleus. Okay, so all the positive protons are densely packed in the nucleus, that the electrons are not stuck, that they're moving. Okay, so he came up with this model here. You see these kind of orbitals going around, and that it's mostly empty space. The majority of atoms, these are much larger than in this image than they really are in real life. Everything here is much smaller than it is, or the picture here shows it to be much bigger than it actually is. So most of the atom is empty space. Positively packed nucleus, electrons moving around, mostly empty space. That's the Rutherford model, or sometimes called the nuclear model. Okay, so that was the model for some time. But Bohr came along and said, here's some issues with the Rutherford model. So if this were true, so you have this electron circling around this positive nucleus, electrons are negative, the nucleus is positive, it's further away and then it gets closer. The problem with that is if it gets close enough to the nucleus, there's going to be attraction there because you have positive and negative. So if this is circling around and gets too close to the nucleus, the electron is literally going to be sucked into the nucleus and possibly cause an implosion of the atom. And if this were true, then we would see lots of imploding atoms everywhere. And we really don't see that very often. So he said, I don't think it could be this rotation where you get closer and further away. I do think the electrons move, but I think the electrons actually stay the same distance as they orbit that nucleus. So they stay that same distance as they orbit that same nucleus. So he came up with the idea of, instead of this kind of like oblong shape, it's more like a circular shape. And so they keep the same distance from the nucleus so they don't get sucked into the nucleus. So in this picture here, you see two colors now, because by this time the neutron has also been discovered. So you've got the protons and the neutrons in the middle. That's all your mass, all in the center there. And you've got positive protons and neutral neutrons, and then your negatively charged electrons orbiting around it, spinning around it, moving around it in what we now call energy levels. This is the model we're going to use most in chemistry, but it's not necessarily the most accurate model. Technically, the quantum mechanical or the cloud model or the Schrodinger model is the technical most accurate. This is why we don't use it though. So here, this picture here, the planetary model is kind of like the Bohr model with the electrons moving around and the nucleus here. And this is the electron cloud model. So you still have your nucleus with your protons and electrons. And instead of having your electrons in like a ring, it's kind of in an area. So here's why. First of all, the Bohr model is a 2D model. That imagines that the electrons are just spinning like this in like an X plane. But why can't they spin in a Y plane? Why can't they spin in a Z plane? We live in a 3D world, so we have to factor that this is not a 3D image. It doesn't factor that in. So the electron cloud is supposed to help us visualize like kind of a bubble around the nucleus. It's anywhere in that area. The other thing, and it's a little complicated, but it's Schrodinger's idea of the cat. So he talked about back in the day that if you stuck a cat inside a box with poison and then sealed the box, do you know if the cat is alive or dead? You actually don't know if the cat is alive or dead until you open the box. So he hypothesized that the cat is both alive and dead and neither alive nor dead. Very psychology-y and physics-y and whatever. The idea there is because space and time do not sync easily. Again, this is like weird physics, so I'm not expecting you to understand this like significantly. If we know where something is in space, we don't know when it is in time. And if we know when it is in time, we can't know where it is in space. That's kind of how they came up with this cloud model. That's great that that's the most realistic model, but it's not the most helpful model that we will use. So we will focus on using the Bohr model to understand how electrons move, to understand the attraction between the two, to understand how different ions might attract each other, lots of things that we'll learn later. But so we will focus in on the Bohr model. Okay, so just to summarize, protons were discovered. They are positive. PP might help you. Protons positive. They have mass and they're in the nucleus. The neutrons are neutral, okay, so the neut might help you, neutral. It also has mass and is in the nucleus. And the electrons are the negative ones with no mass. It's very, 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 very much smaller than the other two, so we don't include it in the mass, and it's orbiting the nucleus. Okay, great, we understand some stuff about atoms, but how does this connect to static electricity, okay? The reason is because of the locations of the electrons, okay? The electrons are on the outside. So in order to get electricity, especially static electricity, we're looking at movements of electrons. These electrons can jump in between energy levels. Sometimes they even jump to another atom. And so that positive part, those protons and neutrons, they're not going anywhere. They're staying there. They can be manipulated, but it takes a lot of effort to get those to move. The electrons can move a lot easier. So when we get static electricity, it's actually electrons moving their location. It could be moving to another energy level or moving to another object itself. And that imbalance is what causes that static electricity. So that is why, if you understand the structure of an atom, then you actually understand why static electricity happens. It's those electrons moving either to an object. When you like rub a balloon on your hair, you possibly are moving those electrons from one object to another, or just adjusting electrons even in one atom as well. So that is a quick lesson, a history lesson, and a little bit of a background on the atom.